Alright, so here we are with our second set of 50 questions at the end of this homework. First one takes us back a few chapters to balancing chemical equations. So in order to do this one, we need to recognize that sodium, there's 1 and then there's 2, so put a big 2 here. That'll match the little 2 there. We now have 2 hydrogens, but water has 2 hydrogens. We have 2 carbons, but here's a carbon and here's a carbon, so together that makes 2. We have 2 times 3, which is 6 oxygens. We have 3 here, 4, 5, and then 6. So now it's balanced 2, 1, 1, and 1. And that matches B. Got to balance it in order to do the rest. What's nice about these next several problems, if the relationship is 2 to 1 to 1 to 1, this next question says, and this is the fastest way to do a problem like this, if the numbers are nice, like this one happens to be, the theoretical number of carbon moles, so carbon dioxide moles is the third number, so looking at this number, if we have 6 here, well 2 is to 1 as 6 is to 3, it's half. 1 is to 1 as 3 is to 3, that's the same, so that's just going to be 3. So you're just matching and repeating that pattern. For this one, same idea. They say now what if, so looking at sodium hydrogen carbonate, what if that one now is an 8? What happens to water? Water in our formula was our last number, so they're looking at this number, so they're comparing that 2 to 1 in this case, or 8 to 4 to 4 to 4, just as 2 is 1 to 1 to 1. So we're looking for that 4. That's the fastest way to do those. I'm going to show you on this next one where it's a little bit tougher how to deal with that. So in this case we can kind of do the same thing. They say 10 moles, so we have 10 moles of that sodium hydrogen carbonate, which was our first coefficient. Now they say mass of water instead of moles, so we just can't cheat off the numbers anymore. So we know that this is 5, 5, and 5, but this would be 5 moles of water, not mass of water. If we take this 5 times the periodic table way, we're done. So you could do that. Let me show you what you could have done on all of these. Take those numbers that they gave you, in our case the 10, if that's 10 moles of sodium hydrogen carbonate, sodium bicarbonate, we need to get rid of moles sodium hydrogen carbonate. Cancel that on the bottom. We want to get to moles of water. If we look at our balanced chemical equation, that was a 2 to every 1. So that was a 2 to every 1. There's the 5 that we got as an answer if we stop here. We're going to keep going though one more step and say if we get rid of moles of water, we can use grams in the periodic table of water. So we're using the coefficient definition, we're using the molar mass definition. This is just H plus O in the periodic table. So 1.01, 1.01, and 16 gets about 18.02. So 10 divided by 2, which is our 5. Take 5 times the 18.02, and you get 90.1. And that's what we want. So this is how you could do all of those. Just plug in the 6 or the 8, 6 or the 8, and then divide by the 1 over the 2. You get the same answer as we did in our head. Either way is going to work. 54, a little bit different. 54 says what happens when you have 1 mole. And the student made 22. So if 22 grams was isolated, that's the actual yield. We need to figure out what 1 mole can make so that we can get the theoretical yield. So we need this number to get the theoretical. And this is going to be something you'll see on a lot of these problems coming up. So when we do this, same setup, but instead of using 10, we're using 1. So 1 mole of sodium hydrogen carbonate. Get rid of moles sodium hydrogen carbonate and go in this case to grams of carbon dioxide. So we're going to do moles of carbon dioxide first. We go to our balanced chemical equation. That was a 2 for sodium hydrocarbonate, just as it was in the other problem. But now instead of doing water, we need our carbon dioxide number, which is that second to the last one. So it ended up being the same. That's not always going to be what happens though. Very similar next, we cancel moles of CO2. We know in 1 mole of CO2 we can get grams of CO2 on the periodic table. That's C plus O plus O. So carbon is 12, oxygen 16 plus 16, so that's 32 plus 12, that's about 44 grams. So we do that, we get 1 divided by 2, which is half of 44 is 22 grams that could be made. They actually made 22, so when you take 22 grams and you divide it by the 22 grams that we found, so theoretical goes on bottom, actual, so actual on top, theoretical on bottom, times 100 is percent yield from our notes. So take this times 100 and you get 100. So hopefully that's your grade on the next test. Tough test though, so 100's tougher on this one. Same idea, but tougher question. So we need to balance this one first. I'll cut to the chase to save some time on that one. You're going to get C, 219. So you're going to get that odd number on water and have to double it. Once you do that though, we can use it on the next one. We have 3 moles of, this is 6 carbons, 12, so it's a hexane. So we'll just call this hexane for short. That's its UPAC name. So if we have 3 moles of hexane, so 3 moles, I'm just going to call that H for short. 3 moles of hexane. We need to get moles of hexane and convert it to carbon dioxide moles. So because the numbers aren't nice here, because they're 2, 19, 12, and 14, that's too hard to do those multiples in our head. We'll just do the one-step conversion process for moles of hexane, not hydrogen. So let's put hex there just to be safe, is what we want. So find the ratio. Hexane was a 2, so put that here. Carbon dioxide was the third, so we need that number, which is 12. So 3 times 12 is 36, divided by 2 is the answer we're looking for, 18. Same idea here, but now they say 1 mole of hexane. So get rid of hexane, moles from the coefficients in the balance equation from above. So that was a 2, just like it was before. We're going to mass of carbon dioxide. We already know that that was 12 moles of carbon dioxide from that one up there. But this gives us moles. We want mass. We need to go that one step further and not only cancel these moles, but cancel these moles. 1 mole of CO2 was 44 grams of CO2 on the periodic table. So that was again C plus O plus O. 12.01 plus 16 plus 60. So 12 divided by 2 times 44. The ones don't do anything other than waste time. 12 divided by 2 times 44. 264. That's what we're looking for. Lastly, they say, what's the percent yield? 1 mole of hexane. Well, we use 1 mole of hexane. They got 22 grams of carbon dioxide. We just found that you can make 264 grams of carbon dioxide. So if you could make 264 grams, you only made 22 grams, you had a big leak because you lost most of your carbon dioxide. 22 divided by 264 times 100 is a very terrible 8.3%. So because we had the same calculation as 57 when we cheated, we used the theoretical on the bottom. So this was the theoretical. And we put the actual on top. Times 100, that was 8.3%. Not very good. 61, very similar, but different. So same kind of question, just different numbers. So again, we need the balanced chemical equation, so I'll cut to the chase on that one. You'll get this one. So we got that one for free. Knowing those numbers, though, we can do 61 to get the answer. Here where they say theoretical mass, so because they say mass and not moles, we can't use the 2's and 1's and convert them to 4's and 2's or 6's and 3's or 8's and 4's or 10's and 5's or anything like that. You could do that one, though, for 60. 61, they have 2 moles of sulfuric acid, so we'll call that SA. Sulfuric acid is the first one, that's this one up here. So they say 2 moles of sulfuric acid, so again, SA for short. We need to get rid of moles of sulfuric acid, and they want mass of sulfur dioxide, so moles of sulfur dioxide will come first. Moles of sulfuric acid cancel. Sulfuric acid was our first number, which was a 2. Sulfur dioxide was our third number, which was a 1. So right now, 2 divided by 2 is nothing other than 1. So it's reduced. Now we got one more step. Moles of SO2 need to cancel. Notice this is getting tedious to some degree. Same kind of setup, just different numbers to plug in. Here we have S plus O from the periodic table. So that's 32 and 32, that's about 64. So 2 divided by 2 is 1 times 64 is 64. And that one's done. Looks easy when I do it, right? But I've done these a while. And I know the pattern. Once you see the pattern, they're easy, but until you see the pattern, they're terrible. 63, this is a full-blown grams to grams. So anytime you have grams to grams, we saw this in the mini lecture, expect 3 conversions. Expect your mole to run across the top of your problem. Get scared and dig deep in your problem because moles like to hide underneath anyway. So here we have 25 grams of fluorine, so put that out front. Grams of fluorine need to cancel. Fluorine moles need to cancel. You can only do that diagonally, top to bottom. They want maximum amount of IF7, so grams of IF7. Grams of IF7 is what they want. That's per mole of IF7 on the periodic table. This is IF7 because we need a balanced chemical equation. Those will also cancel. So this setup is completely normal for grams to grams, or next week for milliliters to grams, or for next week grams to liters for gases. So very common setup to have something like this. These are just 1 because these are periodic table. This is F plus F. This is I plus 7Fs. So periodic table wise, fluorine, about 19. So 18.99 rounded up, so about 19 times 2. So that's about 40, so about 38. And then I times 7Fs, iodine is 126. So 126.9 plus 7 times 19 for fluorine. We get 259.9 from the periodic table. Now we need the coefficients for our mole ratio. Those are either subscripts or coefficients. In this case, we have a chemical equation, it's just not balanced. So what does 2 and 7 have in common? Well, it's 7 and 2. 2 i's, 2 i's, 2 times 7 is 7 times 2. So this is a 172 reaction. Iodine is not used. Fluorine is, and it's on the bottom, now it's a 7. IF7 is a 2, that's on top. Now we're ready to multiply across the top, divide across the bottom. I like to go in sequence, multiply, divide, multiply, divide, multiply, divide. 25 times 1 doesn't do anything, divided by 38 times 2 divided by 7 times 259.9. Hit enter. Very long problem. Answer 48.9 roughly. Hiding over there deep. Very common setup for grams to grams. 4 milliliters to milliliters next chapter. 4 liters to liters next chapter after that. 2 on this page left, we have limiting reactant, so which one runs out first. In these kinds of problems, I just like to pick one and then solve for the other. You either have enough or you don't. So I'm going to pick the first one because it's first. If we have 6 moles of hydrogen gas how many moles of O2 do we need? We have 4. Do we have enough? So let's cancel moles of H2. This is much like in the PowerPoint with the cheesecake example. We need moles of O2. In the balanced chemical equation, it says we need 2 H2s for every imaginary 1 O2. So 6 divided by 2 says we need 3 moles in order to use up our H2. So we need 3 moles of O2. We have 4. We have enough. So which one runs out first? Which one runs out first is hydrogen, because when hydrogen's used up, it's going to use 3, but we have 4. So oxygen is the excess reactant. It could use up to 8 moles of hydrogen gas, but we only have 6, which is why it ran out first. Very similar but different kind of problem coming up next. They want who is excess, so who's left over. So it's like if you have cheese and bread, when you make grilled cheese, one runs out before the other. This is the exact kind of problem. So again, I'm going to pick the first one and then solve for the second one, see if I have enough. So 10 grams of calcium oxide. Grams of calcium oxide have to cancel. 1 mole of calcium oxide you can find on the periodic table. That's Ca plus O. Calcium on the periodic table, 40.1 roughly. So 40.1 plus another 16 for oxygen, rounded up over here. Probably do that one in my head, so that was 56.1, and then we need to get to moles of H2O because that's what they gave us in the problem, so we don't need to go any further to grams or anything like that. So we need moles of calcium oxide to go away, we need to get to moles of water and stop, compared to 3. In the balanced chemical equation, we have 1 calcium, 2 oxygens, 2 oxygens, 2 hydrogens, 2 hydrogens, so this is a 1 to 1 to 1. So this is just 1 calcium oxide to 1 water. So I didn't really do much other than cancel some units. We're left with moles of H2O. We're going to compare to 3. We either have enough or we don't. So 10 divided by 56.1 times 1 over 1 doesn't do anything. We get 0.178. So 0.178 moles of water is used up when all 10 grams combines to make calcium hydroxide. So we need 0.178. We have 3. We have way too much. So in this case, water is in a huge excess. We have over 2.8 and some change left over. We only use 0.178 of those 3. Number 67 used to be a bear of a problem, but then I cheated. I gave you a hint that said lemon lime is limiting. So if you find lemon lime soda up top, it says that 2 liters is what's going to run out first. So they gave you this big long pantry list or grocery shopping list of things to get. But we're saying from the get-go that looking at that, our lemon lime is going to run out first. So we're going to use that as our conversion. So when we do this, we need to know that 2 times 2 is 4. So that's 4 liters. So we need 4 liters, 2 times 2 liter bottles, per 50 servings. So there's our conversion. 4 liters of soda per 50 servings of fruit punch. They're saying what happens in our situation when we have 8 2-liter bottles. So 8 2-liter bottles would be 16 liters. So we take 16 liters. Notice as it's set up, it's not going to work. You're going to get liter squared, so you're going to have to invert that one. Every 4 liters is 50 servings of fruit punch. Liters of that lemon lime soda cancel. 16 times 50 divided by 4 is what we want. And we get 200. So it's a terrible problem if you have to go through and find the limiting reactant. I gave you the hint so that you didn't have to. Otherwise you have to calculate how many servings each ingredient could make And then after 15 or 20 minutes, you find out limit line is the one that runs out first. I saved you that amount of time. You're welcome. 68 through 71 is a beast. So I'm going to speed it up by jumping to 69 first so that we can use its answer to answer 68. This is grams to grams. When we did that before, on a previous problem, we had this set up. So we're going to use that numerous times in this section, just with different numbers. We have 2 grams, so we're going to have 2 setups. So moles on top, top and bottom, and on bottom, as expected. Moles on top, top and bottom, and on bottom as expected. We have 78.1 grams of O2, so grams of O2 per 1 mole on the periodic table. O2 cancels. The balanced chemical equation, O2 was a 13. O plus O is 16 plus 16, that's about 32. So far so good. Let's do the other one. 62.4 grams of butane, so I'm just going to call this capital B to make it a little cleaner. Grams of B for butane. Moles of butane, so this would be 4 carbons plus 10 hydrogens. 4 carbons is 4 times 12, that's 48, plus another 10, about 58.1. So that's 0.1 times 10, so that's why that 0.1's in there. This is butane. Butane was a 2. So far so good. Now they said grams of CO2. So grams of CO2, grams of CO2, grams of CO2, 1 mole of CO2 on the periodic table. C plus O plus O, we did that in a previous problem. That's 12 plus 16 plus 16, that's 32, that's 12, so that's 44. Same there, same conversion. We need moles of CO2. Find CO2 in the balanced chemical equation, that's 8. Those coefficients always used in the middle. Notice grams cancel, moles cancel, moles cancel, grams cancel, moles cancel, moles cancel as we need. So much like our lab when we made aspirin, whichever one makes the least amount of butane is the answer to 68 because it is the used up first reagent, but it's also what theoretically predicts the answer to 69. So by doing this, we saved a little bit of time. So to the calculator, 78.1 divided by 32 times 8 divided by 13 times 44 says we can make 66.1, which is a choice. Happens to be the smallest choice there, so it has to be the answer. We'll come back to that when we prove it. The other one, 62.4 divided by 58.1 times 8 divided by 2 times 44 with a whopping 189. So we have enough butane to make 189 grams of CO2, but we only have enough oxygen to make 66.1, so this is all that's actually possible because our butane will be left over in excess. So 66.1 answers this one, but it also tells us that oxygen is the one that produces the theoretical, so it must be the one that runs out first. So 2 down, 2 to go. In the next one, they say that you made 50.1. If you made 50.1 grams of CO2, you could have made 66.1 grams theoretically. Times that by 100 to get that answer a little bit faster. 50.1 divided by 66.1 times 100 to get 75.7%. So one more in that series, they say how much butane was accessed. They didn't say it was butane because they wanted you to find that in 68. But now we know there was butane. So we know this is how much we have. We just need to solve how much oxygen consumes butane. So instead of using 8 moles of CO2, let's change this to a 2 and change this to a butane. If we change this to a butane, because it's the same gram to gram kind of setup, we would just change this to butane. We already know that was 58.1. So this is 58.1 grams. Let's see how much that is. So 78.1. It's not the answer, but I think it is a choice. This is how much is used, not how much is left over. 78.1 divide 32. Times it now by 2 because we're doing butane, not oxygen, not carbon dioxide. 32 times 2, you got to divide by 13. We have multiplied by 58.1. 21.8. So 21.8 grams of butane is used up. So if we have 62.4 grams of butane, we just took 21.8 and used it in the reaction with oxygen. So the difference is what's left over. 62.4, subtract 21.8. So notice, don't take the bait. That was how much was used. Subtract that one, you get 40.6, which is the answer. That's a long one. Requires 2 steps to get to 40.6. 73, we have 1 mole of methane, half the mass of a mole, or same mass as half a mole of oxygen. So just be careful that they're talking about oxygen gas. So 1 mole of methane, 1 mole of CH4 is 12.01 plus 4 times 1.01. So it's about 16.04. Half a mole of oxygen, they did not say oxygen gas. So half a mole of oxygen atoms is what they're assuming. So that would be half of 16.00. That's only 8. So because they said half of oxygen, not half of oxygen gas, which would have been half of 32, which would be 16, which would be true. So trick question. This one's false because this is O, oxygen gas is O2. So be careful with that. 74, 1 mole of carbon monoxide is the same mass of 1 mole of nitrogen gas, so 1 mole of carbon monoxide would be 1 mole of CO, and this would be 1 mole of N2. This would be 12 plus 16, which is 28. This would be 14 plus 14, this would be 28. So that one is true, within rounding error. The number of atoms in 1 molecule of ammonium dichromate is 17. So the number of atoms in 1 molecule, so that's just the subscript, so you don't have to multiply by Avogadro's number because it didn't say mole of anything. We have 2 nitrogens. We have 2 times 4, that's 8 hydrogens. We have another 2 plus another 7. That would be 10 plus 2, which is 12, plus 7, which is 19. That's not 17, so that's false. They're assuming that you probably didn't add up the 2 nitrogens, maybe, I don't know. But it's not 17. One mole of ozone is 1.8 times 10 to the 24th atoms. So in order to deal with this one, we need to deal with Avogadro's number. 1 mole of ozone has 3 atoms. So 3 moles of oxygen atoms in O3. For every 1 mole of anything, oxygen included, there are 6.02 times 10 to the 23rd atoms. So 3 times 6 is 18. Times 10 to the power 23, but that's not in proper scientific notation. You need to move that back, and that's going to be 1.8 times 10 to the 24th, which is what they have, so true. So far, so good on that one. And number 82, we have 21.2 grams of KBr is 0.17 moles. So the easiest way to do that is remember molar mass is grams per mole. So if we have 21.2 grams of KBr, take grams of KBr and get rid of it. This you can get from the periodic table. That's K plus Br in 1 mole of KBr. Potassium on the periodic table is 39.1. So 39.1. Bromine is 79.9. So 39.1 plus 79.9, 119. And then now we divide 21.2 divided by 119, and we get 1.77, and that's pretty close. So true. '83, the molecular formula for a compound is CH2O. Molar mass of 120 is C3H6O3. This does reduce to a 1, a 2, and a 1, so that part's true. It can reduce correctly to the empirical formula CH2O. Does it weigh 120? That would be 3 times 12.01 plus 6 times 1.01 plus 3 times 16. If that adds up to 120, then we're good. So 3 times 12.01 plus 6 times 1.01 plus 3 times 16 is 90.09. They say 120. So I say false. Alright, on to some matching. Home stretch of this monster homework just about over. If you've been with me for almost an hour, thanks, because it's a lot of practice, a lot of good practice. Here we have the number of atoms. So this was back to our first page, just a matching section based on it. So here what we do is take 3 times the n, so we have 3 n's. 3 times the 4, that's 12 h's. We have 1 phosphorus, and we have 3 oxygens. So just remember to multiply across. So we have 3 plus 12, that's 15. We have another 4, so together that's 19. And that's our answer, B. So do 2 more just like that. 88 through 90, just add them up on the periodic table, find their masses underneath their symbols, and then add them up. You'll get that one pretty quick. The rest of them are all percentages, which are a lot of what we did in our hydrate lab at the end. Take piece divided by the whole on all of these. So from here to 100, piece divided by the whole times 100 equals a percentage. So this one says nitrogen percent. So take 2 n's divided by the whole, which is the entire N2O molecule, so 2 n's plus O in parentheses times 100. So in reality, what does that look like? That's 2 times 14.01 on the periodic table, 2 times 14.01 on the periodic table again, plus 16 in parentheses times 100. And for 91, you'll get 63.6%. To do that exact same thing for the next 2, I'll set them up for you. I just won't calculate them for you. One's going to be a match, but for NO2, remember it's piece divided by the whole. So nitrogen divided by nitrogen plus 2 O's times 100. Plug them in from the periodic table just like we did above, and you'll get a different answer for this one. That kind of gives it away. But then you have to go to the next one, do the exact same thing for calcium cyanide. Just remember, this is a 2 and this is a 2 when you multiply across. Still nitrogen, so it's 2 nitrogens divided by calcium plus 2 carbons plus 2 nitrogens in parentheses times 100. And see which percentage you get there. Very same thing here. Percentage sulfur, so take sulfur divided by sulfur and 2 sodiums. Sulfur divided by 2 sodiums, sulfur and 4 oxygens. And then very similar on this last page, more of the same. This one's a little bit easier because once you get one, you know the other. As long as they didn't try to trick you by giving you 2 of the same, but they are different. So once you get this one, you'll get the next one for free. This one said percent carbon, so take the piece divided by the whole thing. So 6 carbons divided by everything, which is 6 carbons plus 8 hydrogens plus nitrogen plus chlorine times 100. Plug in those letters for the weights on the periodic table and you'll get the answer straight across. So you already know what the other one's going to be as well. We'll do the exact same thing for that one. 6 carbons divided by 6 carbons, 8 hydrogens, 2 oxygens, 2 nitrogens plus sulfur, and you'll get the other one. There's a lot of repetition to do these when it matters on the exam later. Lastly, percentage oxygen, same thing as before. Take the piece and divide it by the whole thing. So 3 O's divided by 10 carbons, 6 hydrogens, and 3 oxygens. Times it by 100. You get a percentage. And in this case, you'll get the lowest, at least the lowest choice percentage, letter C. Do that for 99 and 100. So piece, 3 O's divided by everything. So 2 nitrogens, 8 hydrogens, 1 carbon, 3 oxygens times 100. Here, take 2 O's divided by everything. So 6 carbons, 8 hydrogens, 2 oxygens, 2 nitrogens, sulfur all on the bottom times 100. You'll get those as well. So that was a beast. Took me almost 10 pages of these edges of papers to get through it. But hopefully it shows you that there is a pattern. Whether it's canceling moles or making percentages, that's the 2 main ideas for this chapter. And it'll be much of the same next chapter. See you next time.